Hi everyone, I'm Ruijia Chen.
And I'm Yuheng Wu.
We are from the University of Wisconsin-Madison and did internships at NaviNote Spatial in London. We are excited to present NaviNote, a last few meters navigation and spatial annotation system designed with and for people who are blind or low vision.
Exploring and understanding one's surroundings is fundamental to human well-being, but this remains challenging for blind and low vision people. For example, in a public square, BLE people may have difficulties figuring out what's around them or where they can sit. Spatial annotations offer a promising approach. They are pieces of information anchored to specific 3D locations. As BLE users explore a space, they can access nearby annotations to get rich environmental context without needing to aim the camera. Prior work, such as footnotes, has explored the benefits of spatial annotations for BLE exploration. However, there remain two limitations. First, these systems typically contain annotations created by sighted people and do not provide an accessible interface for BLE users to contribute their own situated knowledge. And second, these systems rely on GPS, which can drift by several meters, making it hard to place or retrieve annotations precisely in space. Two emerging technologies may bridge these gaps. First, large language models can empower conversational interfaces, allowing BLE users to interact with the system simply by speaking. Moreover, recent advances in visual positioning systems, or VPS, can localize a user's position and orientation with sub-meter-level accuracy using just a smartphone. VPS achieves this by matching camera data with a pre-scanned map of the environment. Combined with LM-powered voice interaction, BLE users can place and retrieve annotation at precise locations through speech. For example, they can say, add a note to this bench, and the system will know which bench they mean from their position and orientation. We want to leverage these technologies to enable BLE users to be active in-situ explorers and annotation creators. We asked three research questions. First, what types of annotations are most valuable to BLE users and in what scenarios? Second, how can we design an accessible interface for BLE users to author in-situ spatial annotations? And third, how can BLE users effectively access and utilize these annotations? To answer the first two questions, we conducted a formative study workshop with 24 BLE participants to brainstorm desired annotations and system features. Based on thematic analysis, we identified 6 types of annotations essential for exploration: safety, accessibility, amenity, layout, attraction, and experience. Guided by these categories, we later preset 39 annotations for our user study. Participants also expected the system to provide precise last few meters navigation. They emphasized that without the ability to reach specific locations, annotations alone would not be sufficient. Based on these findings, we designed NaviNote, a voice-based system that combines VPS for precise localization with the agentic AI architecture. To enable hands-free interaction, NaviNote runs on a smartphone mounted on the user's chest with the camera facing forward to continuously track their position and direction. Users can talk to the system via earphones. NaviNote supports 3 core capabilities: question answering about the surroundings, last few meters navigation, and annotation access and authoring. First, users can ask questions about their surroundings. NaviNote synthesizes information from multiple sources, including the camera image, the internet, and the annotation database to generate answers. This allows users to ask questions at different levels. For example, general scene understanding questions like, what's in the park? Or more specific ones like, what's in front of me? Second, inspired by the formative study, NaviNote provides precise last few meters navigation. Users can ask NaviNote to guide them to a very specific location within the area. Using the camera and depth sensors together with annotations related to obstacles, NaviNote detects walkable areas and generates turn-by-turn instructions. It also provides an audio compass for constant direction confirmation, a beeping signal that plays louder when users are facing the correct direction and softer when not. When available, NaviNote also guides users along the haptic path, which are physical structures like walls and curves that can be followed with a white cane. Now let's watch an example.
Can you guide me to the statue?
Waiting for response. 10 o'clock for 6.4 meters. The destination is at 12 o'clock, 14.2 meters away. Correct direction, 4.9 meters. 10 o'clock for 5.0 meters. Follow the edge of the flower bed to your forward left. Arrived at the statue. The destination is at 12 o'clock, 5.7 meters away. The statue is located inside a flower bed.
NaviNote also supports annotation accessing and authoring. To reduce information overload, NaviNote provides layered annotation access. Safety and accessibility annotations are played automatically, and other types will trigger a brief notification that users can choose to listen or to ignore. Users can also change how they want to hear each annotation type. Let's see an example.
11 o'clock. Watch out for the podium. It's close to the flower bed's edge.
Users can author annotations by speaking. For example, mark this board as having uneven ground. NaviNote integrates VPS, camera, and annotation data to identify the reference location and place the annotation accordingly. The annotation can then be shared with other users. I want to create a note saying there are pink flowers in the center of the square.
Waiting for response. Your note has been successfully created, stating, there are pink flowers in the center of the square. Let me know if you want to make any changes or need help accessing it.
We aim to understand how effectively NaviNote enables blind or low vision users to access, utilize, and author spatial annotations. We conducted a user study with 18 blind or low vision participants at a public square. The study had two parts. First, we compared navigation performance between NaviNote and TapTapSee, a widely used app that provides on-demand concise image descriptions. Since no existing tools addresses last few meters navigation for blind or low vision users, we chose TapTapSee as it can describe objects crucial for navigation. Participants navigated to comparable routes with the two systems. Then, they freely explored the square using NaviNote, listened to our preset annotations, and created new ones in situ. We analyzed the data quantitatively and qualitatively. We found that compared to TapTapSee, participants had a significantly higher success rate reaching the destination using NaviNote. They found NaviNote's audio compass and turn-by-turn instructions easy to follow, as they provided constant confirmation and correction of their direction. For example, participant 6 said, NaviNote was correcting me when I was going wrong, and instructions in feed making it easier for me to understand how far I was from where I was going. Participants also found spatial annotations valuable for understanding the square. They remember significantly more landmarks with NaviNote than TapTapSee during navigation. During free exploration, the annotations provided a general impression of the square's layout and available amenities. As participant 15 recounted, with NaviNote, I learned that there are branches, benches, statues, flowers, and people sitting around. Beyond accessing annotations, all 18 participants successfully created new annotations using NaviNote. Most annotations fell within our original 6 categories, validating the formative taxonomy. Moreover, 3 participants also created annotations to request information from other users. For example, participant 14 left an annotation asking others to help identify the statue in the square. We therefore added the request as a 7th category to our taxonomy. Our findings also suggest design implications for future spatial annotation systems. We highlight 2 points here. First, crowdsourcing scanning and VPS boundary transition. NaviNote assumes that VPS scans can be collected by volunteers or automated platforms. However, VPS coverage is still limited. Future systems should support smooth transitions between VPS and GPS to maintain continuous guidance across environments. Second, keeping annotations aligned over time. As environments change, annotations can become outdated. Advances in 3D change detection could help identify mismatches when users rescan the space and trigger realignment or removal of outdated annotations. In summary, our contributions include: first, NaviNote, a voice-based system for spatial annotations and the last few meters navigation for blind or low vision users. Second, an evaluation of NaviNote with 18 blind or low vision participants. And third, a taxonomy of desired spatial annotations. Please see our paper for more details. Thank you.